Hello everyone, this is part 2 of the project management tutorial. This time we're going to be working on problem 2. So this company is preparing for a total quality control training for its employees, and the activities required for the preparation are listed here, along with the normal activity times, the crash activity times, the normal cost per activity, the crash cost per activity, and the immediate predecessor of each activity. For question 1, we're going to be graphing the activity on node diagram. We're going to be determining the critical path and the completion date of the project. Okay, for now, we're going to be ignoring this part of the table. We're going to be focusing on the activities, their normal durations, and their immediate predecessors. This is a pretty simple network. We have activities A, B, and C with no immediate predecessors. So we start our network with a dummy start activity with duration 0. And we have activity D preceded by activity A, activity E preceded by activity C. And of course, to close off our network, we add a dummy end activity with duration 0. As usual, we start with a forward pass to find the earliest starting times and the earliest finishing time of each activity. So we have activities A, B, and C start at time 0 at the earliest. So their earliest finishing time is going to be 0 plus their durations. We have activity D preceded by activity A. So its earliest starting time is equal to activity A's earliest finishing time, equal to 6, and its earliest finishing time is equal to 6 plus 5 equal to 11. Same thing for activity E. It's preceded by C, so its earliest starting time is equal to activity C's earliest finishing time, equal to 4 plus 8 equal to 12. As for the end activity, its earliest starting time is equal to the maximum between the earliest finishing times of activities D, B, and E, which is 12. 12 plus 0 equal to 12. There is no delay allowed in the project, so the latest starting time, we're going to be starting the backward pass here and finding the latest starting and latest finishing times of each activity. So the latest finishing time of the end activity is 12 minus 12 equal to 12. For activities D, B, and E, which are the immediate successors of the end activities, all the latest finishing times are going to be equal to the end activity latest starting time, 12. To find the latest starting time, we just subtract the duration from the latest finishing time. For activity A, the latest finishing time is going to be equal to activity D's latest starting time, 7, minus 6 equal to 1. Same thing for activity C. It has one immediate successor, E, so its latest finishing time is equal to 4, minus 4 equal to 0. Okay, now for the start activity, the latest finishing time is going to be the minimum between the latest starting time of activities A, B, and C, which is 0. Okay, so now that our network is completed, we're going to be determining the critical path, which is, as we talked about the other time, a path that goes through the critical activities, which are activities with 0 slack time. That means that their earliest start is equal to their latest start. For our network, we can see that the only two activities that satisfy this criterion are C and E. Thus, our critical path would be this one. As for the project completion time, it is 12 weeks after the starting date of the project. The second question is the total cost required for completing the project on normal time, which is simply the sum of the normal cost of our activities, which is equal to $2,700. Now to the last question. We wish to reduce the project duration by 3 weeks. So which activities should we crash? So we know that for the project duration to be reduced, we need to crash activities on the critical path, since it's the longest path in the network and its duration is the shortest possible time in which the project can be completed. Okay, so when we choose which critical activities to crash, we need to look at two things. First of all, if the activity can be crashed. This means that its crash time should be shorter than its normal time. And second, its crash cost per period should be the smallest. If we look at our table, we can see that both activities C and E can be crashed since their crash time is smaller than their normal time. This means that if we allocate more resources to activity C, we can reduce its duration from 4 weeks to 3 weeks. And if we were to allocate more resources to activity E, we can reduce its duration from 8 weeks to 5 weeks. Now we need to compare the crash cost per week of activities C and E and pick the most cost-effective alternative. So for activity C, if we were to complete it in the normal time of 4 weeks, it would cost us $500. If we want it to be completed in 3 weeks, it would cost us $600. So that's a $100 increase in cost for a 1 week reduction in duration. As for activity E, it costs $100 to be completed in 8 weeks. And if we want it to be completed in 5 weeks, we would have to pay $1,600. So that's a $1,500 increase in cost for a 3 weeks reduction. This means that for 1 week, for a reduction of 1 week, the additional cost is gonna be 1,500 divided by 3, which is $500. Now let's compare the costs. We crash activity C by 1 week for $100, or we crash activity E by 1 week for $500. Of course, we choose activity C since it's the cheapest. We go back to our network. Of course, reducing the duration of C by 1 week changes its earliest finishing time to 3 weeks, which changes the earliest starting time of activity E to 3 and its earliest finish to 11, which eventually reduces the project duration by 1 week. Of course, the latest finishing time of activity D have changed to 11 weeks, so its latest starting time is equal to 6, which means that activity A's latest finishing time is equal to 6 and its latest start is equal to 0. This means that both A and D are now critical. So we now have two critical paths, AD and CE. So now to reduce the project duration even further, we need to crash activities on both of these paths. So let's start with CE. We've already crashed C once and it cannot be crashed again, so we have no choice but to crash activity E. As for the second path, AD, both A and D can be crashed, so we're gonna have to compare their crash cost per week. For activity A, the additional cost is $100. For activity D, it's $300 over 2, which is $150. So crashing A is cheaper. Thus, we're going to be crashing both A and E simultaneously. So we crash activities A and C as we did for the previous crash, and now the project duration is reduced to 10 weeks. And no additional critical paths have emerged this time. So we have one more crash to go and we still need to crash both paths. For CE, we're gonna have to crash E again. We have no choice. As for AD, we can see that we've already crashed activity A to the maximum time it could be crashed. So we have no choice but to crash activity D. Okay, so after crashing D and E, we have successfully reduced the project duration by 3 weeks. Now we're gonna calculate the additional cost incurred by the crashing. So we crashed activity C by 1 week. That cost us $100. We also crashed A once, that's another $100. Activity D was also crashed once, so we add $150. And finally, activity E was crashed twice, so that's $500 times 2. That makes the total additional cost $1,350. Okay, so that's it. We're done with problem 2. Please don't hesitate to let me know if something is not clear, and thank you very much for your attention.